Welcome, my digital pathology trailblazers. I'm so happy to see you again. I am ready with the next edition of DigiPath Digest.
Learn about the newest digital pathology trends in science and industry, meet the most interesting people in the niche, and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
Today, we are having, first one is deep learning model shows pathologist level detection of Sentinel Node Metastasis of melanoma and intra-nodal nevi of whole slide images. Then we have cross-modal deep learning for predicting pathology complete response to neoadjuvant chemotherapy in breast cancer. And we have something called global bibliometric mapping of the research trends in AI-based digital pathology for lung cancer. And then we have Pathology Foundation Model. We have a new foundation model. And at the end, we're going to talk about annotations. So let me know where you're tuning in from. Also, if you're viewing this as a replay, leave a comment and let me know where you're tuning in from so that I can see who is joining, where you are joining from, and let's dive into it. So let's start with the deep learning model shows pathologist level detection of Sentinel Node Metastasis of melanoma and intra-nodal nevi, I don't know how to pronounce it, on whole slide images. This is frontiers in medicine, and I decided I'm going to be looking up the impact factors. This is impact factor 5, and this is Jan Sharov et al. From the group is from Sweden and Finland. Sweden and Finland was checking those detection of those metastases. So what happened here? Nodal metastasis in sentinel node biopsies is crucial for melanoma staging. However, intranodal, so we're talking, once again, we are talking about melanoma. The entity here is melanoma, and there is something called nodal metastasis. So this is in sentinel node biopsies, where you take a biopsy from the closest lymph node to the draining lymph node from the lesion, and it's crucial for melanoma staging. So intranodal nevus, INN, may often be misclassified as nodal metastasis. So this is like a normal thing, intranodal nevus, that looks very similar. And this can lead to potential misdiagnosis and incorrect staging. And not surprisingly, there is high discordance among pathologists. We know there is high discordance always. This is like the placeholder sentence that everybody is going to have in a paper about AI and pathology. The pathologists are discordant. Well, yes, they are. But this is still amazing job that they are doing. But if we can have a tool that helps us, fantastic. So there's high discordance among pathologists assessing those SNB, sentinel node biopsies, for positivity, which may lead to false staging. So what do? We use digital pathology, and there is potential for implementing AI. And we checked, the group checked the capability of AI to detect nodal metastasis and intranodal nevi in those biopsies. So it's 11th DigiPath Digest. I was supposed to buy a tablet and I didn't yet, but I will. So what did they do to check if AI is going to be better to distinguish nevi from nodal metastasis? They had 485 H&E whole slide images. That's not a huge amount of slides, but that's okay. If they can show stuff on them, that's good. So they included nodal metastasis and the nevi, the intranodal nevi, from 196 biopsies. And that's very nice, something that, I mean, is a standard, but when digital pathology started, it wasn't a standard. They divided the slides into training, 279 whole slide images, validation 89, and test 117. And the deep learning model was trained with manual pixel-wise annotations. So here we run into the gold standard paradox. They start the paper with, oh, pathologists are discordant. But what do you train the model on? On pathologists' annotations. How many pathologists annotated? I don't know, because we would need to go to the paper and check exactly. So the AI, but that's, just keep that in mind when reading those papers. The AI and three blinded that was for assessment, not for annotations. 3 blinded dermatopathologists assessed the test set with, this is super cool, fantastic, they had immunohistochemistry serving as the reference standard, which is fantastic. Let's put a smiley here, because then you have an independent method and not just pathologists, right? But let's see what happened. The AI model showed excellent performance, and the area under the curve receiver operating characteristics of 0.965 for detecting what? Nodal metastasis, so not the NEVA yet. And in comparison, the AUC for nodal metastasis among dermatopathologists ranged between 0.94 and 0.98. So we are at the same level. This is fantastic. Here, maybe we can, so here and here for the pathologist, and for the detection of intra-nodal nevi, the AUC was lower, not surprisingly, for both AI 0.781 and dermatopathologists, which ranged from 0.63 to 0.79. You know what? Whenever I see these like comparison, I think like, oh, how do those pathologists who are, you have a range, right? 0.63 to 0.79. How did the pathologists who had 0.63 feel? Because I sometimes take part in those, interpathologist comparisons, and I'm like, oh, what if I'm the worst pathologist? But you know what? People choose researchers with like similar backgrounds, or on purpose with different backgrounds. And this is still valid, but I'm always thinking in the back of my head, oh, if I like miss something that others didn't miss, or like, how do I compare? They usually don't tell you. At least they didn't tell me when I was part of those studies. But anyway, the conclusion here is that the AI model showed excellent accuracy in detecting nodal metastasis and achieving dermatopathologist level of performance in detecting both the metastasis and the nevi, which is fantastic, because then we have a tool that can augment pathologists, but further validation is warranted. A good exercise. I like this one. And yeah, when you start joining, if you were a little late or if you were watching the replay, please go ahead and comment. If you also have questions or something that you want to investigate, let me know in the comments. Investigate me to investigate in those papers. One thing that I did yesterday, I had a webinar. I was part of a webinar, gave a presentation, and one thing that I did for the people who joined the webinar was I gave them the slides. I mean, these are not really slides, but this is a PDF of my notes on those abstracts that we're reviewing. But if you guys would like that, if you would just like a copy of this, let me know in the comments. Just put slides or slide, whatever, slides, and I'll send it to you. I'll figure out a way so that you can independently download it, but I'm going to reach out to everybody who comments. So if you want the slides of this presentation, let me know what's in addition to the stuff that you would get from PubMed anyway. So I put those names of the papers, what the impact factor is, and also you'll have some notes of mine. So when there are concepts that are not so clear, then I will highlight them, and I have a special color code. I'm going to tell you about it. But in the meantime, let's talk about cross-modal deep learning model for predicting pathologic complete response to neoadjuvant chemotherapy in breast cancer. And this is NPJ Precision Oncology. So what I had to check, actually, what's this NPJ? And it's Nature Partner Journals. But I checked the impact factor. This is 7.9. And who is working here on this paper is Jianming Guo et al. And this group is from China, Harbin, China. What happened here is pathologic complete response. I love the abbreviation PCR, like polymerase chain reaction. Pathologic complete response. And I don't know if there are any guidelines for creating abbreviations in papers, because they seem to be just like freestyle. Whatever you write there and then put the first letters, that's your abbreviation for the rest of the paper. That's okay. So this PCR, pathologic complete response, serves as a critical measure of success of neoadjuvant chemotherapy. And of course, it's going to be abbreviated NAC in breast cancer, directly influencing subsequent therapeutic decisions. Measure of the success of neoadjuvant chemotherapy. So how do you measure success, right? And when? So what they explored, they want to accurately predict the complete response. So it has to be before it actually happened, right? So they propose a cross-modal multi-pathway automated prediction model that integrates temporal and spatial information, so time and space. And this model fuses digital pathology images from biopsy specimens and also ultrasound, multi-temporal ultrasound, so at different time points, and to predict PCR status early in the therapy. So they start the therapy. So what happened? They start the neoadjuvant therapy, chemotherapy, and then they measure immediately. And this model demonstrates exceptional predictive efficacy. And we don't have any more information in the abstract. I somehow trust it because it's 7.9 impact factor. But basically, I thought this was interesting. Usually, like, you do retrospective studies. I just haven't seen it. Maybe it's common, but maybe it's not. But I thought, okay, they start the therapy, then they measure both the biopsy and ultrasound, and they can come up with a prediction. And they say that personalized treatment paradigms based on this model is the foundation for personalized treatment based on individual responses. So that was the takeaway from this one. The next paper that I wanted, and see, guys, we didn't go live on Instagram and I couldn't do it today, but next time we will. And next time we will go live on TikTok as well. So if there are any digital pathology trailblazers on TikTok, let me know. Another interesting paper that came to my inbox was called Global Bibliometric Mapping of the Research Trends in Artificial Intelligence-Based Digital Pathology for Lung Cancer over the past 2 decades. And let's see if I can see. Yeah, so here's my color coding. I was like, okay, bibliometric. I kind of know what that is. They probably looked up all the papers and they checked the trends, right? And now they didn't use LLMs, large language models, but now you could basically take all those publications and analyze it with ChatGPT and ask for trends, which is a super insightful thing to do. So this bibliometric mapping is an analysis. Bibliometric analysis is a statistical method that studies scientific output and the networks behind it. It's used to analyze patterns of publication within a specific period of time or body of literature. So basically, that's what I thought it was, but it's actually an official discipline. So the Dan Xiong from China, Guangxi, China, was the first author, and his team did that, or her team. I don't know if it's a male or a female. But what happened here? The rapid development of computer technology has led to revolutionary transformation in AI-assessed healthcare. I would like to see this revolutionary transformation. Definitely revolutionary advances in research. But where is it? Maybe it's in China. I have not visited China. So maybe it's there. Actually, I did talk to one Chinese company and they were very advanced compared to what I know from the rest of the world. So I'm taking back these words. Let's just focus on this paper. So the revolutionary transformation in AI-assisted healthcare, but there is a lack of comprehensive scientometric analysis in this field. I didn't know it was a word, scientometric. So bibliometric is probably part of this. Scientometric, there was an analysis of 197 publications, like in 20 years, 197 related to digital pathology in lung cancer from 502 institutions across 39 countries, published in 97 academic journals in the Web of Science Core Collection. So I had to check what is the Web of Science Core Collection. I mean, it's some kind of literature collection, right? But and this is so this is the green thing is our color coding for explanations. So if you guys want some explanations and the slides from this, then give me a slide in the comments or slides, and I'm going to send those slides to you with all my scribbles if you want that. So the Web of Science Core Collection is a database that contains information on scientific content, impact, and collaborations. It's considered to be the world's most trusted citation index for scientific and scholarly research. Okay, so they did this, the Web of Science Core Collection between 2004 and 2023. And did we check the impact factor for this one? No, we didn't. Sorry, I already said we didn't. But like 197 papers only in 20 years, that's not too many papers. But that's okay. Let's analyze. So, which were the leading countries? United States. I need this one. United States and China were leading as the paper authors, the primary research nations. And in this field of pathology of lung cancer, current research primarily consists of independent studies. That is a problem among countries, emphasizing the necessity of strengthening academic collaborations and data sharing between nations. Well, maybe not only academic, right? Why would you only do academic research? Research in the industry can happen as well. But okay, so we need to strengthen because it's always like one cohort, not always. Very often, a cohort of some patients, some data, some images that you have access to, a cohort of patients that you have access to, and then this is what you publish on, right? So this is like a super localized to your healthcare institutions. Now with foundation models, we're doing better, but most of those papers were just published on like some small cohort of patients, and no wonder because we have few papers. I don't know if this sentence made sense. Anyway, so it's fragmented, it's separated. So the current focus and challenge related to this digital pathology lies in enhancing the accuracy of classification and predictions through improved deep learning algorithms. That was the main thing, I would say, in the last decade, to like have a specific diagnostic application of an algorithm and then making it on par or more accurate than with comparing it to a pathologist and saying, oh, it's better than pathologist, or it's more consistent than pathologist. Then it kind of annoys the pathologist guys. Sometimes it doesn't annoy me, but I'm very used to this stuff already. But anyway, like all those papers say pathologists are bad, they're inconsistent. I don't know what else, but you know what? Pathology is the gateway to the rest of the medicine, especially in oncology, but in everything else. But I would say when I have seen it, only now we are going beyond like single application, single diagnostic application, and making it more efficient. So, but and now the integration of multi-omics studies, let me go back on this one, presents a promising future research direction. So like the ultrasound thing, like we can integrate more data points, especially the data points that are less invasive than pathology. If you can like have the biopsy at the beginning, which will have to be there, you cannot omit the pathological morphological diagnosis, but maybe you can reduce the frequency of the biopsies, right? So include ultrasound, so multi-omics, and exploring the application of digital pathology in immunotherapy for lung cancer patients was also a new trend. The next paper that we have today is called a Pathology Foundation Model, guys, our favorite topic, hot topic, foundation models for cancer diagnosis and prognosis prediction. So we have already in the title, we're talking about diagnosis and prediction. Nature, many of these appeared in Nature. Many papers of these, like many, I don't think there were more than 10. So out of those less than 10, many were published in Nature. So definitely a hot topic, definitely a hot method. This paper was, the first author is Xue Wang, and apologies for maybe my mispronunciation of Chinese last names or Asian last names. We have an impact factor of 50.4. Nature, we know that, right? That Nature is high impact factor. And there was a group from Boston, Stanford, and different cities in China, Chengdu, Guangzhou, and several others. And we also have part of this group was Pennsylvania State University, Hummelstown, Pennsylvania. I used to live there near Hummelstown. My husband used to work in the Hershey Medical Center in Hummelstown. Okay, so let's talk about the concept of foundation model. We extensively talked about it in our foundation model live stream, and if you haven't listened to that one, it's on YouTube on the podcast. I would need to check which number that is, which I will by the end of this presentation. Foundation model, right? Foundation model basically is something that has a lot of slides it was trained on. Before I give you a context, we're gonna go through this abstract. So standard artificial intelligence methods for histopathology image analysis focus on optimizing specialized models for each diagnostic task. We just said that, right? Each diagnostic task, one model. This is what was being done, which I think is super useful as well. But there are so many diagnostic tasks, like you could spend like 5 scientific lives, or I don't know, cats have 7 lives, so maybe scientists have also a lot of lives. You could spend all those lives addressing each single diagnostic task with a model. So those methods, of course, have limited generalizability to images generated by different digitization protocols or samples collected from different populations. We just said that too from the other paper, that it's very fragmented, localized to a specific population. And here they address the challenge with the clinical histopathology imaging evaluation foundation. Couldn't be any other way than find a fantastic acronym for this: CHIEF. I thrive on analyzing those acronyms. So CHIEF is the new model. We had Virka. I don't know what else we had. We had several of them. I should have put them here. So our CHIEF is a general purpose weakly supervised machine learning framework to extract pathology imaging features for systematic cancer evaluation. CHIEF leverages 2 complementary pre-training methods to extract the pathology representations. It is unsupervised pre-training for tile-level feature identification, unsupervised, and then we have weakly supervised pre-training for whole slide pattern recognition. So we have unsupervised and we have weakly supervised, unsupervised, and weakly supervised. Unsupervised is pre-training for tile level feature identification, and the weakly supervised is for pattern recognition. If you're still joining, let me know where you're tuning in from. What happened here? We did what did this chief do? It's like supposed to do everything, but actually it did cancer cell detection, tumor origin identification, so like which tissue it comes from. I would need to go in because you can recognize it by which healthy tissue is next to it. But if it's a metastasis, then you can't. So I would need to go into this paper, and they for sure explain it because it's a Nature paper. Every reviewer would have asked that. And then also molecular profile characterization and prognostic prediction. So we have 4 tasks: cancer cell detection, tumor origin identification, molecular profile characterization, and prognostic prediction. And they validated Chief using less than 20,000 whole slide images. And here we're going to go to our data from the presentation about large language models. And 19,491, so less than 20K, it was validated on 32 independent slide sets collected from 24 hospitals and cohorts internationally. So that's international effort. We have international group as well. And they say Chief outperformed the state-of-art deep learning methods by 36.1%, showing its ability to address domain shifts. So observed in samples from diverse populations and processed by different slide preparation methods. So this domain shift, or like different domains, are exactly like the cohorts of slides that are similar because they were stained in one batch, and then a different batch was a little bit different. So you have like a domain, this staining domain shift, or it was a certain population, then it was deployed on a different population, on slides from different populations, and it didn't perform quite as well because the domain was shifted. So this actually accounts for the domain shift. And Chief provides a generalizable foundation for efficient digital pathology evaluation for patients with cancer. And now let's go to our homework from large language models. So here we say Chief was using 60,000 slides. That's a lot compared to TCGA, the Cancer Genome Atlas, because it has 40K slides. Here we had over 60 and 90 different anatomic sites. 19. The natural image foundation models, like those that classify natural images, dogs, cats, and everything that's like in the normal world and not under pathologist's microscope, they use hundreds of millions. But according to Hamid Tizush from his presentation and his talks, well, and also comparing to Virkov, misspelled, which is another foundation model that used 1 million slides. This one is smaller. My conclusion is this one is smaller. Whether we can call it foundation model, we don't know because there is no clear definition. But basically, I just want to put it into perspective. This TCGA 40K slides, here 60K slides was used, and Virco, a different model. And according to different scientists, we would need at least, so Virco was 1 million. What Hamid Tizush says, to achieve the performance of those natural image foundation models, we would need 5 million. We don't have 5 millions here, but still amazing work. And so if you're anywhere else, please give it a like. If you have any questions, let me know if you have any questions. And we have another publication about annotations. If you have ever annotated medical images, give me an A in the chat. Annotations, And at least one person in the audience did together with me when we were doing a lot of annotations. So improving the annotation process in computational pathology, this paper was a pilot study with manual and semi-automated approaches on consumer and medical grade devices. And this is Journal of Imaging Informatics in Medicine 2.9 impact factor. So semi-automated, I would have given a lot for semi-automated when I was annotating in 2017, 18, 16. Giorgio Casaniga et al. And this is a group from Italy and also some collaborator from Cologne, Germany. So the development of reliable AI often relies on ground truth provided by annotations of whole slide images. And this is time consuming and boring, honestly. A comparative analysis of different annotation approaches is performed to streamline this process. Two pathologists annotated renal tissue using semi-automated segment anything model. And we needed to check what that is. The segment anything model is called SAM. This is an AI model from Meta, from Facebook Meta, that can cut out any object. So this is for natural images, but they used it. So there are two pathologists annotated renal tissues and using semi-automated SAM model and manual devices, touchpad versus mouse. I don't know how they compared everything, but okay, so they had manual devices, touchpad and mouse, and then comparison was conducted in terms of working time, reproducibility, overlap fraction, and precision. And what did they find out? That, also the impact of different displays on mouse performance was evaluated. Okay. So the annotations focused on 3 compartments. Tubules, 57 annotations. Guys, that's not many annotations. Glomeruli, 53 annotations. And arteries, 58 annotations. Maybe 50 whole slides? I don't know. But 7 annotations, that's not many. The semi-automated, maybe it was enough to check what they wanted to check, and then they didn't make the pathologist annotate anything unnecessarily. That's thoughtful as well. So the semi-automatic approach was the fastest. Surprise, surprise. No surprise there, right? Of course, it was the fastest because, not of course, because if the model was not doing a good job, the SAM model, it wouldn't be the fastest. But it was the fastest and had the least inter-observer variability, averaging 13.6 minutes with a difference of 2%, followed by the mouse and the touchpad. The highest reproducibility in tubules and glomeruli was achieved with SAM as well, overlap values of 1 and 0.99 compared to 0.97 for the mouse and 0.94 and 93 for the touchpad. I liked the touchpad. I liked annotating with the touchpad a lot better than the mouse, so I would need to check what kind of touchpad it was. And then though SAM had lower reproducibility in arteries. So here a model is underperforming in detection of a particular structure, and then it's not helpful anymore. So I take back my words that, surprise, surprise, of course it was better. Well, if it's not performing, then you have to correct a lot of it, and then it's not better. And they say using non-medical monitors increased annotations times by 6.1. I don't know, you only did 57 annotations. I'm going to go into this paper and check exactly what they did, how they did, and what kind of so here's the statement, non-medical monitors. what were the specs of your monitors, because often the specs of the non-medical monitors now for gaming are better than the specs for medical monitors that have to be like approved, cleared, and their development cycle is a lot longer. And that is it for today. I don't have any more papers for you. Question, if anybody wants those notes from me, give me a slide comment in the comments. If you are watching the replay, please do that as well. I will be sending the slides to whoever wants them. Thank you so much for the likes. Thank you so much for joining and staying till the end. If you are listening to this on the podcast, feel free to give us a good rating on the podcast, and I talk to you in the next episode.